this computer. All right. Okay, it's recording. Thank you. So my committee consists of Professor Carrie Kahoy, who's the chair. She is Professor of Aeronautics and Astronautics here at MIT. Dr. Kritika Devaraj, who is Vice President of Avionics and Spacecraft Technology at Planet. Professor Olivier de Weck, Professor of Astronautics and Engineering Systems here at MIT. And my external evaluator today is Dr. Steve Chen, who is Technical Group Supervisor of the AI Research Group at NASA JPL. And Ishil Demir is my reader, who is Vice President of Mission Systems at Planet. So introductions to me, I did my undergraduate degree at Imperial College London. I did my master's degree here at MIT. I've been in Carrie's lab for a long time, starting as an undergrad and then a grad student where I did some optical design and machine learning as different research projects. For just under 2 years, I worked as an edge compute and machine learning engineer at Planet, where I worked on edge compute system design, some camera sensor selection, and some vision system design. And my academic status at MIT, my GPA is fine, and I have almost completed all the PhD requirements. I have 2 left, one for my minor and one for my math class, which I'll be taking next semester. So the high-level summary of my proposal today is to use a look-ahead instrument and computer vision to improve the scientific and imaging return of tasked Earth-observing satellites through onboard schedule reoptimization. So if I have a satellite that looks like this and has a primary instrument that is pointing nadir like this, there's lots of different kinds of Earth observation missions, but generally they fall into 2 main categories for the big players. There's monitoring missions where essentially you try and image as much as you can when you can, and there's task missions that follow a schedule of preordained tasks that are optimized on the ground or in space, however. So a monitoring mission has a very wide area coverage, but a slightly lower resolution, but because it's imaging all the time, it has a slightly more rapid response. In contrast, the task mission has a narrow area coverage and higher resolution because of all the data budget considerations, but it requires external input to direct tasking. What I'd like to get to is something called a dynamically tasked mission, and in this case, I have it such that a forward-looking secondary payload scans upcoming tasks, an onboard compute system reprioritizes the schedule, and the primary instrument then executes that reoptimized schedule and captures its resulting imagery, and ideally this results in higher effective throughput of useful data, especially for uncommon phenomena. So why bother doing this on board at all? So conventional Earth observation struggles with unpredictable phenomena, and I've grouped these into high-frequency detractors and low-frequency attractors. So high-frequency detractors are things like cloud cover, which covers about 2/3 of the Earth's surface at any one time and definitely shows up in lots of tasked Earth observing satellite missions. And low-frequency attractors, there's been some research into the dynamic targeting applied to deep convective ice storms and planetary boundary layer science. So onboard dynamic tasking addresses both these scenarios at once, but in my proposal, I'll generally be considering cloud cover and removing tasks rather than adding the back end. I consider that an extension. So jumping straight into my literature review. I'm gonna do some definitions first, so I'm not chasing a moving target throughout this presentation. So dynamic targeting I define as the ability to use a perception system to observe upcoming tasks, analyze and reoptimizing the schedule based on the utilities derived from those observations, and then finally use a primary instrument to execute the reoptimized schedule. So this is just one idea of autonomy. There's lots of different mission concepts that can spawn from this singular idea. So in terms of concepts, I've just shown you onboard look ahead, where we use an onboard payload to reassess task utility. There's also the idea of using a fused web of sensors throughout the Earth to reassess task utility. You could use a virtual look-ahead instrument like a geostationary satellite like GOES or Himawari to reassess task utility in real time. And also something like a leader-follower constellation where a leading spacecraft essentially scouts upcoming tasks and informs a follower spacecraft. Of course, there's lots of different types of missions that you could come up with. There's almost no limitation here. And the latency of each mission concept, the idea of onboard look ahead, something that's on the horizon takes about 20 to 90 seconds to come to nadir depending on your altitude. Something like a leader-follower constellation, depending on your exact mission configuration, you can have a information latency of about 1 to 30 minutes. With something like a geostationary satellite like GOES, you have up to 30 minutes information latency, but given at a 10-minute cadence. Something like a sensor web, this is an absolutely huge and broad idea, so it really depends. It can be minutes to hours and depends on things like if you have inter-satellite links or not. Compare that to a conventional task mission where you might have 5 to 20 hours of information latency depending on how your schedule is formed, depending on your ground stations, their locations, and depending on where they are in the schedule. So one last definition that I'd like to cover is I make a distinction between dynamic targeting versus dynamic tasking. So dynamic targeting, I say, is the ability to acquire, analyze, and generate a schedule or trajectory based on inputs from a perception system in a single overflight. Whereas dynamic tasking, I define as acquiring, analyzing, and being able to modify a pre-optimized schedule from the ground based on inputs from a perception system in a single overflight. This work covers dynamic tasking formulations with a body-fixed look-ahead sensor incorporating agile look-ahead as part of the schedule. And just to make sure I've doubly defined all of those terms, dynamic tasking, I define it as above. Body fix, I define as a non-steerable, so no phase array look-ahead sensor, for example, a body-fixed camera. And agile look-ahead, I define as adjusting the spacecraft attitude to get better observations of upcoming tasks. So why now? This is certainly not a new concept. Having your spacecraft be smarter is not new. NASA, CNES, JAXA all independently came up with the concept in around the turn of the millennium. But what's really changed and probably the most significant impact is the amount of compute available on Earth-observing spacecraft. So JPL EO1 had a lot of groundbreaking AI science and applications demonstrated on it, had about 4 million instructions per second of compute assigned to the autonomous sciencecraft experiment and only 128 megabytes of RAM. Contrast this with something like UpSat in 2019. It has an Altera FPGA with 2 hard ARM cores, and importantly, its payload computer is separate from the flight computer, so you can effectively use all that compute without disrupting mission operations. Capella has been launching Jetson TX2 GPUs on all its spacecraft since Sequoia in 2021. That has about 30 trillion integer operations per second and 8 gigabytes of RAM on board. FISAT 1 and 2 launch with an Intel Movidius Myriad 2 vision processing unit. It's a little bit different from a GPU. It's a little bit more oriented towards computer vision tasks. And Planet is launching its Pelican 2 with the Jetson platform on it. And I'll be honest, that one's me. I got to work on that with a bunch of very talented people, which I'm very grateful for. So here, there's definitely a trend towards more compute and specifically more compute tailored for computer vision applications. So some notable autonomous missions. JPL EO1, and I'll do a deep dive of these right afterwards, did a whole bunch of interesting applications of AI in space, launched in 2000. The DLR Firebird mission, a lot of AI things were proposed for that mission, but not demonstrated, but that was launched in 2012. GoSat 2, probably one of the most successful demonstrations of dynamic targeting, launched in 2018. And finally, OPSAT, which is a flying laboratory where researchers can test the code, demonstrated a few vision applications in 2022, 2023 or so. So JPL's EO1 spacecraft hosted the autonomous sciencecraft experiment on board. It has a hyperspectral instrument actually made by Lincoln with 400 bands. It had 4 MIPS and 128 megabytes of RAM, and because of those compute limitations, it had only about 12 of those bands assigned to the ASE. It did follow-up observations using the Casper onboard planner, and it had a lot of firsts in space, including the first demonstration of machine learning-based computer vision, such as a support vector machine-based classifier for active volcano monitoring, as well as things like a random forest and Bayesian thresholding classifier demonstrated for cloud screening a little bit more recently. DLR Firebird is a mission that launched in 2012. It is a 2-satellite constellation. It has sorry, I have a typo here. That should be a space then. A lot of proposed dynamic tasking formulations were developed for Firebird, but not specifically demonstrated. It is a mission for detection of surface temperature anomalies and wildfires. A greedy planner with considerations of resource bounds were developed for Firebird, but like I said, never actually shown in space. GoSat 2, like I mentioned, has probably the best demonstration of dynamic targeting so far. So it has a 5-band spectrometer plus a red, green, blue look-ahead sensor. And importantly, the look-ahead sensor its pupil is connected to an electronically steerable fold mirror. So it can essentially repoint and do look-aheads for free. It takes very little power and resources to do it. So the onboard cloud screening algorithm that I show down here, sorry, can you see my cursor? I hope so. Thanks. So GoSat 2 will look at an initial task, it'll do cloud screening, and then do intelligent pointing to the area where it has the most cloud-free, the area with the least amount of clouds in that image, and then it will take an image through there, and this resulted in a 71% increase in obtaining cloud-free imagery as compared to without intelligent pointing on GoSat. OPSAT had especially a whole bunch of different vision demonstrations. There was a dynamic targeting formulation from JPL utilizing cloud screening and target pointing planning that was never flown. I think OPSAT deorbited it a little bit too soon, but essentially it uses the leading section of the primary instrument field of view as the look-ahead for replanning and uses a combination of the JPL Casper and Eagle Eye solvers. So now going into the literature review. So I consider dynamic tasking a fusion of heuristic design, and specifically I mean the ability to estimate the resources and costs of performing a look ahead, computer vision on spacecraft, naturally being able to figure out what you're looking at, and Earth observation task scheduling, where I lie in the center of all of these. So a whole bunch of different papers on this have been proposed, and I will point out the specific clusters related to the missions that I just presented on. So these are EO1 and EO1 adjacent papers. These are papers relating to GOSAT-2. These are papers relating to OPSAT. And finally, these are papers relating to the SMICES mission concept in JPL. I'm going to do a deep dive into scheduling and the Earth observing, let's say, image pipeline, and then come back with a little bit more of gap analysis and then start going into my approach. So the spacecraft imaging pipeline, it starts with pre-processing and then scheduling the observations that you're going to be doing. So this requires tessellation of imaging requests from customers into points. It requires, with an orbit propagator, converting those requests into imaging opportunities, and you'll definitely have more than one imaging opportunity per request. And then from those imaging opportunities, you can generate a schedule optimizing to the parameters however you see fit. The spacecraft then executes the schedule. There's very limited contact with the ground station. Steve, as you pointed out, even worse than a remote control car. There might be some possible intermittent contact through inter-satellite links, though. And finally, when the spacecraft is finished executing the schedule, it'll downlink its data, it'll post-process it, which means auto-rectification of imagery, rejection of missed tasks. So, for example, tasks might be missed due to cloud cover, or the spacecraft might simply run out of resources, and you kind of abstract missed tasks as binary. Is this image good or is this not? And this isn't really in scope of this work. Dynamic tasking doesn't really affect the post-processing stage of any of this, so I'm going to be focusing on the pre-processing and scheduling here. So the reason why scheduling is so difficult is that spacecraft essentially do not have infinite resources. We have to conserve power, we have to conserve data, and also we have limited ability for us to reorient the spacecraft in between captures. So here is a summary of previous scheduling methods. In this case, I have not considered federated scheduling, as the onboard scheduler is really a core part of my work, but federated scheduling is a little bit of an extension of this. The tightest constraint of all the ones that I showed you is definitely agility. So it's considered by every single one of these previous papers. Data and power considered to a different extent. About 2 of these are actually in operation. So Augustine's 2016 work on using a mixed integer linear program for doing scheduling that morphed into the Planet scheduling system after years and years. Ishmael, you're very familiar with that. And Eddie's 2021 work on maximum independent set scheduling. It's unclear if Capella's using that, but he was also the vice president of missions at Capella, so it's likely they're using that. I'm going to go through for the most common scheduling methods on this plot. So the first is using a greedy algorithm. So this is the simplest scheduling method of them all, which is where you take a locally optimal action at every step based on a heuristic. This is great. No backtracking is performed, so it's very easy to incorporate resources like batteries and things like onboard storage, which depend on your total trajectory. It's computationally very efficient, but it's unlikely to result in optimal schedules because it can't see the big picture. But the nice thing is it's extensible to constellations, as each spacecraft can take locally optimal actions. The next on this list is mixed integer linear programming, which is the most widely used method for spacecraft scheduling. It's extensible to all kinds of scheduling problems. There's a whole bunch of hyper-optimized mixed integer linear program solvers available. It's trivially extensible to constellation scheduling by adding additional mutexes, but its big drawback is that costs and constraints must be linear. One workaround to this is by discretizing the pointing attitudes, but this gets complicated pretty quickly. The other extremely nice thing about mixed integer linear programming is because it's a convex solve. That's not quite true. The solutions can be verifiably optimal using a mixed integer linear program, so it's very useful to compare the optimality you get from a MILP to other scheduling methods. Graph traversal, if your constraints are transitive, for example, agility, you can represent it as a graph with fixed edges, and your schedule can then be obtained by finding the longest weighted path in this graph. This only works if you consider only agility. Power and data become very difficult to incorporate in the scheme. You can also consider this, rather than graph traversal, as finding the maximal independent set of non-feasible tasks, which results in you being able to find a schedule faster, but without any guarantees of optimality. The graphs are usually very dense, so the combinatorial complexity kind of explodes, but if you use horizon planning, you can also use that to trim transitions far in the future to combat this density. It's great for interacting with a human. Augustine demonstrated this in 2014 about having a human being able to manually slot tasks in and out of a schedule. And finally, the newest and well, quite interesting is reinforcement learning, specifically Monte Carlo tree search. So this is the most expressive scheduling algorithm. You can represent continuous transitions of spacecraft state, and you can also very interestingly model things like attitude-dependent resources. So power, which is dependent on the solar incidence on your solar panels. So MCTS with a value function learned with reinforcement learning was used in AlphaGo to beat Lee Sedol in 2016, and it's a great way of trimming the search space so that suddenly tree searches are more feasible. It's trivially extensible also to constellations in the joint action space, but its combinatoric space is massive, and the naive MDP formulation is done per time step. So having a tree branch out every second for a space mission becomes just absolutely huge and dense extremely quickly. All right, so now I'm going to talk a little bit about computer vision and the assumptions that have gone into previous dynamic tasking work. So previous work usually utilizes varying levels of assumptions either in the concept of operation. So for example, assuming your spacecraft is at nadir when it's overflying all its tasks, or it makes some assumptions in specifically the camera model. So Damiani in 2005 made assumptions in both of these. So he assumes that the spacecraft is always at nadir when overflying a task and is also, I'm going to open the chat so I can see it. At nadir when overflying a task, and also that when a task goes over a specific push broom line, that its utility is instantaneously obtained. Lenzen in 2014, as part of development for the DLR Firebird mission, used a projective model. So this is a real camera model. We're using a prospective projection formulation, the highest fidelity that we have. Chen in 2015 created pointing heuristics for being able to reorient the spacecraft to observe upcoming tasks. Candela in 2023, as part of the SMICES mission, assumed a windowed look-ahead function where you'll have a square track in the across and along track areas that you can observe. And Imasu, as part of the GoSet2 pointing and intelligent pointing and developments, used this kind of, how do I say this? The electronically steerable mirrors. So essentially your pointer becomes free in this case formulation. So in terms of gaps, there is a gap in integrating agile look ahead, so the ability to reorient the spacecraft to get a better vantage point of upcoming tasks with scheduling algorithms for satellite imaging constellations. And that's what my approach is going to go into now. So going through all that literature review, you start getting natural research questions that we wish to answer based on agile look ahead integrated with constellation scheduling. The first is, how do we combine agile look ahead actions with the scheduler? And the second is, how much better can we do compared to a conventional task mission if we add agile look ahead? This is an important question to answer because agile look ahead is taking away agility from imaging actions. So it's important to see at what point is the benefit greater than the costs. So now I'm going to start going into my approach. For my approach, I'm going to start off with talking about the assumptions of my spacecraft configuration because I can't talk about anything else without talking about like what I've assumed. So for my approach, I'd like to assume a 4-SkySat constellation with 52-degree inclination with the same agility parameters as used by Eddie. They're completely fake numbers, but they are good for comparison. I said 52 degrees inclination because that is the inclination of SkySat 16 through 21, and also it means that I can sometimes use an analytic propagator instead of doing sun synchronous and having to consider J2, which is very nice for computational tractability. I've assumed a look-ahead sensor with a 50 by 40 degrees rectangular field of view based on a preliminary systems analysis that I put in my proposal documents, and I've assumed arbitrarily a 20-degree field of regard on my primary instruments. I've assumed that the spacecraft is fully actuated in every direction. I'm utilizing a constant acceleration and deceleration agility model, and I am not considering the accuracy of the vision model. That's a can of worms that I don't have data to be able to answer, really. I'm assuming that if a task is observed, that we can assess its utility with 100% accuracy. And finally, I'm assuming that the onboard data model consists of a pre-optimized schedule from the ground, as well as a priority queue of tasks that we wish to incorporate in the schedule should we have the opportunity. So data sets, I want to make this as applicable to commercial satellite demand as possible. So I'm using the 10,000 largest world cities as a proxy for global satellite demand. So here I plotted the 10,000 largest world cities, and here I plotted a map that Planet once released of where SkySat collects happen. And qualitatively, these are quite similar, so I'm happy with using this as a baseline, but Steve, you also, thank you for that, gave me the Eagle-Eye dataset of tessellated city points, which I'm also interested to use because that simulates another part of the spacecraft imaging pipeline. So my contribution overview. Sorry, my animation was messed up. My first contribution is I don't really have software that lets me be able to answer these research questions immediately. So I like to construct an end-to-end dynamic tasking simulation framework, which I'll get to in a bit. Secondly, I'd like to consider, and it took me quite a while to find the words for this actually, is to consider agile look-ahead activity generation with both rule-based and learned heuristics. So creating heuristics so that I can estimate how much better would I do if I did a look ahead here compared to if I just continued with my schedule and just continued imaging. And finally, I like to implement these heuristics with onboard scheduling algorithms for constellations. And I'll be honest, the main thing I want to analyze is the gap in if I have inter-satellite links versus if I don't, how much do I gain? So really a systems analysis there. So contribution one, my end-to-end dynamic tasking simulation framework. This consists of two software packages. The first is the schedule simulation. So it consists of image request and collect generation, an orbit propagator, a camera simulation and a world model, a simulation of tasking, so being able to run it through and say this task is included or not. And then finally, the onboard data model and scheduler, so the simulation is as close to the real world as possible. The really nice thing is I can reuse a lot of code from Eddie. The image request and collect generation was probably at least like a couple months of code that I could lift straight from Eddie. He emailed me his code, so that's great. The second part about this is just a reinforcement learning sandbox for my learned heuristics in contribution 2, which I'll elaborate on in a second. This consists of a rigid body dynamics gym environment in OpenAI Gym, and it consists of an actor-critic reinforcement learning model. There we go. The rigid body dynamics environment, I can extend from Patrick McKean in Starlab. I also did a bunch of this work for my project for undergraduate robotics last semester, so that's in a pretty good place. Contribution 2 is agile look-ahead activity generation with rule-based and learned heuristics. So agile look-ahead, depending on your spacecraft attitude, your ground track can change tremendously. So the higher an optimizer angle that you're at, you get much, much larger set coverage of your upcoming tasks, but it comes with costs in that you might have to reorient your spacecraft, and the captures you might get of upcoming tasks will be lower resolution because they're from further away. So how do we combine agile look ahead with the scheduler when it has a completely different action space? So the scheduler can be kind of likened to finding the longest directed path in a graph or tree, and the look ahead action space can be kind of considered a set covering problem where you're planning attitudes to cover and observe upcoming imaging activities. And when you combine these together in the direct transcription, I'm going to say some words that a computer scientist never wants to hear. This turns into a non-convex mixed integer program, which is computationally intractable for the amount of data volume that commercial imaging satellites are hosting today. So instead, what I want to do is I want to do a similar approach to Augustine and Shreeyam, where I want to essentially develop some kind of heuristic to be able to link these two together, to be able to treat look-ahead actions as any other action in the scheduler action space. If I limit myself to greedy look-ahead, that's much more feasible. I'll get into that in a second. So the rule-based policies that I want to consider, like I said, there is a trade-off between looking very off-nadir and having much, much larger set coverage. In this case, you may be able to cover more and more tasks with a single look ahead, which is great. That's what you want. However, the reorientation, the lower resolution are drawbacks. The other idea of this is like if you perform a look ahead as late as possible to minimize the distance to the task, you might have the highest resolution, but you're kind of constrained by this agility constraint surface here. So this line is the distance to my target, this axis is my distance to overflight, and this line represents the trajectory to an imaging task there based on your pitch and roll angle. Oh, sorry, my label is covered. And this constraint is the agility constraint surface, so which is how late I can do a look ahead before I have to whip my spacecraft back around so that I can actually image what I'm looking at. I'll accept a lot of feedback on how I'm presenting this information on this slide, I'll be honest. I haven't found a good way to do it yet, but the rule-based heuristics that I wish to consider is, first of all, the simplest idea. These first two, they don't require any changes to a ground station, so they can be demonstrated in space without any big engineering infrastructure development on the ground scheduling system. So the first is, if I left my look-ahead instrument always enabled, how much could I do? How many tasks could I observe? How much could I modify my schedule? That kind of thing. The second is if you have a case where you have like an expensive look-ahead instrument, something like a very, very high power radar, what if I limit myself to only performing one look-ahead at the optimal time, but without adding any reorientation or agility into that? Then I get into some methods that start changing the spacecraft orientation. The first is if I have a single shot, so I can only take one capture, but I'm using the leftover agility in between the schedule to perform my look ahead, what's the best I can do? The last is if I had as much agility as I needed to perform the optimal look ahead, what's the best I can do? And finally, if I use something like reinforcement or learning with a learned heuristic, how good can I do that? So the really nice thing is we can actually generate all these possible look aheads with their own resource costs and their own rewards, utility, sorry, and have the scheduler pick the optimal one at each step in the future should we want that. So learn heuristics, they're really cool. You don't need to make the same assumptions as above. So for example, in all the rule-based policies, I was constraining myself to one look ahead per upcoming task because that makes the optimization problem tractable. Instead, a reinforcement learning framework with a hybrid action space can go ahead and learn this and spit out a sequence for you. And you can modulate your reward based on the reward structure here. So for example, if the utility of imaging a task I is C sub I, and if it has a probability P sub I such that it's cloud-free, then your reward for covering that task with your look-ahead instrument can just be the sum of C sub I 1 minus P sub I. Like I said, reinforcement learning is very well suited to this hybrid action space where you have both continuous and discrete actions, such as spacecraft motion and also taking a picture at discrete times. And I like to use an A2C, so advanced actor critic method, because rather than just having just the actor, which learns action A's from a specific parameterized policy, actor critic can also estimate the rewards from that policy and can also estimate the resource requirements for that. So contribution 3, onboard scheduling algorithm with the look-ahead heuristics for constellations. So now that I've got these heuristics and I can generate my look-ahead actions at each step, at an example of a graph scheduler, at each search node, I can figure out my feasible transitions to my image action, and I can also generate all my possible look-ahead actions and then go ahead and create a schedule on board from there. Initially, I'm going to have the ground schedule set up that it randomly assigns tasks as occluded in their hidden states. And the hidden state is only uncovered to the onboard scheduler when a look ahead is performed in the simulation. And I think this is fine because the set of randomly distributed occluded tasks is actually much larger than the set of physically realizable occluded tasks on Earth. So it's kind of a harder problem that I'm training on here. And I'm going to baseline it for doing a greedy scheduler, a graph scheduler, and a mixed integer linear programming scheduler. Some simplifications we can make. The onboard scheduler only needs to consider activities whose utility can change, which means that the activities that can be observed by the look-ahead instrument, which means that we only need to consider the local subgraph between the spacecraft's freeze period and the Earth horizon, because those are the observable actions. I'd also, like I said, like to analyze the effect of delayed networking. So how much do we gain from having inter-satellite links versus how much do we lose if we constrain having information only transferred through ground stations? So my expected results, if I have a total number of captured images on this x-axis and the proportion of cloud-free images on the y-axis, if I have a conventional scheduler and it has x sub naught number of images that it captures with about, let's say, 33% of them cloud-free based on data that we have from MODIS, that's as good as it does hit. An omniscient scheduler, if it knows all the hidden states, can get to up here. Obviously, we're never reaching that, but it is a nice approach to be able to bound our results in between the conventional and the omniscient cases. Our region of improvement subtends this triangle here, where we're actually taking more cloud-free images than we would with a conventional scheduler. And for my heuristics, as I presented before, I expect them to form this kind of Pareto front, where the heuristics that reorient the spacecraft and use agility will shift towards the left this way because they're taking away agility that could be used for imaging actions, but you're still resulting in a more cloud-free imagery being downlinked because the information from those heuristics provided to the schedule. So my progress today, I've completed my world model. I have my world model in ECI plus WS84 geodetic coordinates. I did some preliminary systems analysis of a look-ahead sensor, which I used for this. I reused task generation successfully from Eddie. I completed the rigid body dynamics simulator as part of my project. And my reinforcement learning heuristic is in progress. I'm presenting that as part of SmallSat 2024. And in terms of descope options, I'd like to either consider fewer rule-based methods, reduce the constellation size from 4 to 2, get rid of the graph scheduler, consider only the greedy plus mixed integer linear programming one. But other than that, I'm open to suggestions. My schedule, I have a schedule up here of basic timelines, but my contribution Gantt chart is down here. Contribution one is really the foundation for all of this. The other contributions cannot really be asynchronously done until contribution one is done, so I'm focusing on that right now. Hope to finish that in August. Contribution two up till the end of the year, and then contribution three, maybe go ahead and try and finish that in August 2025, and then go ahead and write as much as I can. So my first paper, I am presenting, like I said, some preliminary reinforcement learning work at Smallset in August. In December, I'll finish my course requirements, and then I'd like to submit that study to JSR. Next year, I'd like to submit some preliminary scheduling work to the International Workshop on Planning for and Scheduling for Space Systems. I think I got that right. And then finalize all my contributions by August 2025 and spend that fall 2025 just writing as much as I can. Here's how it feels to write a PhD proposal. And that concludes my presentation. Let the grilling begin.
All right, thank you very much, Shreeyam. That was a lot of content. So now normally what we do is we round robin among the committee members to ask Shreeyam questions. Usually we do one or two each and then pass on to the next person and go until we have about, I would say 15 or 20 minutes left. It's a 90-minute calendar block, hopefully. Does anybody have, before we start, does anybody have any other time constraints that we need to be aware of? The nominal end time is 4:30 p.m. Eastern or 1:30 p.m. Pacific. So if there are any other time constraints, just let us know and we can try to take those into consideration. Otherwise, I will kick off the questions with Shreeyam. You mentioned considering intersatellite networking. Can you, it sounds like you're just planning on doing that for planning information between the satellites as opposed to data.
Sorry, Carrie, I think I didn't hear the last part of your question.
Oh, the intersatellite connectivity for satellite constellations. It sounds like you were planning to analyze the performance with and without it, but intending to use it just for planning and tasking information between satellites as opposed to data delivery to ground stations. Is that correct? And could you comment a little bit more about your plans?
Yeah, that's correct. So I'd like to be able to essentially only transmit the utility information of tasks in the schedule to the constellation and analyze the effect of delayed networking there. I think data modeling, I'd like to have an approach, I think same as Bianchesi in 2007, where he actually has some kind of limit on the duty cycle that can be devoted to imaging. We can use something like, I don't know, like a 10% duty cycle to imaging as a baseline. So not quite high fidelity data modeling, but still considered in the scheduler, if that makes sense.
Okay. My second question, and then I'll hand it off to is you didn't mention anything about periodization of data based on quality. Is that something you're going to be doing? Because you mentioned free, but I imagine that there's a spectrum of free and also higher value of there. How will you incorporate that into either heuristics or your algorithms?
Okay, Carrie, I don't know if it's just me, but we cannot hear you at all. You're cutting out.
Yeah, sorry, I couldn't really grab that question.
Okay.
I think we lost you.
Oh no, I can hear you really clearly. So it's a little confusing. Can you hear me again?
It is very choppy still.
Okay, let's hand it off and I'll hold it better in a second.
Why? I have a couple of questions, so maybe I can go next and we can come back to Carrie. I think she dropped.
Yeah, I think she said she can hold that one in and come back to it. So yeah.
Shreeyam, I wanted to go back to one of the very first slides you showed about the attractors versus the two phenomenon, right? Like the high frequency detractors and the low frequency attractors. So it makes sense that you. Okay, so in a you have these models. The low frequency attractors are by definition very rare.
Yep.
So whereas the high frequency, you have a ton of data set with these high frequency detractors. So as you consider model development that both avoids clouds but targets these low frequency attractors, how do you create a model that, you can use a machine learning based model for high frequency detractors. It's going to be really hard for you to get a training data set for the low frequency attractors using the same technique. So how do you see these two fitting together within a single model, or are they completely separate models that you run?
I wouldn't say they're completely separate. I'd say they're joined like a Y. They kind of end up being the same in the end, but the pre-processing steps are a little bit different. So I kind of only want to consider, like you said, there's only really a lot of data for like cloud cover, that kind of thing. Low frequency attractors are low frequency by definition. I think if you were going to do that, you could plug it into this framework, but you have to develop a different type of mission and you have to schedule your look-aheads in a different way. You're almost to cache these low frequency events, you almost want to have your look-ahead sensor imaging as much as possible, rather than in this case where I'm planning my look-aheads to image my upcoming tasks. So I think it's an extension, and I can see how you do it with the same tools, but this is a cop-out answer, but I'm going to consider it by not considering it, if that makes sense.
Okay. Yeah, I think for essentially a lot of the science problems where you can envision having a look ahead instrument that catches these phenomenon that then tips a higher value instrument.
Yeah.
I think that's a much harder problem than
Yeah.
the first problem, which is to avoid something that is frequent, right?
I'm not convinced it's a harder problem. I agree it's a different problem.
Different problem.
Also,
Okay.
just as a side comment, I'll make the comment that even for a low frequency rare attractor, if you have the right data set, you could actually have a lot of data. So for example, if you chose a low frequency attractor and you had a geo data set, just because it's a very small percentage of the Earth is having a deep convective ice storm, if you're looking at the whole planetary disk, like a weather satellite, you could actually get a fair amount of data.
Okay.
So I have a separate side question, but Devika, did you want to continue or?
Yeah, I can continue. My second question was around your background research literature review. So I think it was really great that you had all these categories of from a sensor web all the way to forward-looking instruments and everything in between. That was a fantastic slide, by the way, that shows the next one.
Oh, this one.
Yeah, this is great. But it seemed like going deeper, you mostly focused on the onboard look ahead based lit review. I think it'll be interesting to also provide a few references to the other models that are not very well discussed anywhere else.
Yeah, I can submit my proposal with some revisions. I did look at that. Steve, you've done a really cool work on using sensor webs for like tasking of, I think it was disaster relief for flooding events and volcano monitoring. So I'll carve out a thicker section in my proposal and
Just a small section to discuss what are the missions. There are some astrophysics like this, the supernova detector. Yeah, that was a good one.
Cool.
Right, so just having some of those added would be great in your
that would be Swift, and then I forget the new one, but if you Google for Swift follow-on, they're looking at exactly that.
Awesome, thank you. Sorry, I hope you can't hear my keyboard.
And I think, okay, just a couple of other small comments. I think you said like spacecraft imaging pipeline. That term's kind of confusing for an Earth observation satellite user. So you may want to, because imaging pipeline refers to what happens after the
yes.
down. So rephrase that to like spacecraft.
Well, or just say onboard imaging pipeline.
Yeah. Or again, like imaging pipeline essentially means like once the image is captured, the pipeline processing steps, Steve, in the conventional lingo. So maybe we want to say scheduling pipeline, scheduling pipeline or something.
That's a better way to put it.
Okay. And then the last question I can think of is really about, okay, so you said you're going to bound. So you had this agility versus power versus
was it this plot, or was it?
No, you had the three. You had your optimization for agility, power, and duty cycle. Like, I don't remember what else, but
It
say
was
Probably
power,
data
data,
volume. Data
energy.
volume, I'm gonna guess.
data
Yeah.
volume. Yes, yeah. So how do you put bounds on these, Shreeyam? Like when you're developing your model, I know you understand Pelican, you know all those constraints, but in general, as you're developing your body of work that could be useful, you can have a large range for each of these parameters. Are you going to bound them? Are you going to make them variable so that it could be adapted? Like, how are you thinking through putting bounds on these?
So I'm thinking, that's a good question. The baseline that I'm gonna do is I'm going to consider like a duty cycle bound, first of all, as like the simplest simplification of all of these. So you can do this many images in a particular orbit, that kind of thing. I think the next level of that is using a greedy scheduler. That is fairly straightforward to integrate all kinds of resource bounds into without delving into too much complexity. So you can say that a solar panel gets a certain average amount of power per second. The onboard data model, one image takes up this percentage of the onboard data model. And with a greedy scheduler doing that on board, I think it's also, I might need to check on this. I think it's also fairly straightforward to have like a incrementing staleness factor. So if you have a very stale, like, data from like the beginning of the orbit doing like first in, first out kind of downlinking, that slots in quite nicely with that paradigm, I think. I think probably what I'm going to stick to is using the duty cycle limitation and saying everything else is an extension, unless you feel particularly strongly about me adding them in at a high
I think you can go at it in multiple ways, right? You can say, oh, I'm gonna like have super broad constraints, so I'm gonna have a power generation model, a power consumption model that takes into account payload power, downlink power, all of that. You can really make it like super broad and make it applicable and parameterize everything. Or you can say, I'm gonna pick a candidate mission. And then you got the spec, I think it can go either way. Doing the former method is a lot more time consuming, but then you parameterize all the variables and it could be applicable to multiple missions.
Yeah.
So again, as a body of work, it might be interesting to not bound it and make a parameterized model. But it's a lot of work. So I will be okay if you just choose a candidate mission instead and constrain your model to that.
I think what I'll do is I'll use the greedy scheduler and have parameterized power models, but they'll be as good as the greedy scheduler can really get. And then what I'll say is for future work, something like MCTS would be able to have extremely high fidelity power models do all this kind of stuff, but I will not be considering that.
Okay. I have one more. Sorry, as I was talking through, one more popped up in my head, but it's really about, okay, once you have the onboard forward-looking imager, you've ingested the data, how are you going to work on prioritizing which schedules important? You have cloud-based detections. What if I have I have ground-based information going up? How do you parameterize that problem and say 30% cloud is acceptable for this priority level versus 20% cloud at that, so they're like, it's a probabilistic, yeah, I don't know how to think through. I don't think you can come up with.
I think you can, I mean, if you have multiple sources of information, you could use something like a Bayesian algorithm to estimate what's like my lowest confidence bound on the utility of this task. That's actually really interesting.
That and following up with what happens to the rejected tasks and how is your algorithm gonna then propagate what occurred, what didn't occur, and like downstream making sure it doesn't get dropped.
I highly recommend going down that rabbit hole. While I agree it's a great problem, that's a different PhD thesis.
I think I don't know if I can share, but some of the stuff I proposed at Planet might actually be fine for that as like the first pass.
Yeah.
Like leapfrog the tasks, but it does come with its own downsides, and that is
each task will have its own metadata, right? You can be very, very naive about it, I think, and this task requires 30% cloud coverage, reject, and then just give the ground information that you rejected it because due to cloud coverage, that's more than good enough.
Yeah.
Yeah, like the whole joke is half the time people are interested in like 4 particular pixels in the image. So this whole notion of cloud cover percentage
Yeah.
that the commercial provider uses to screen whether or not they get a retake is actually somewhat meaningless, right?
I think
Yeah.
the fact that I abstracted the vision model very greatly also gives you a lot of control to slot whatever you want in there. So Kritika, we had a patent for like cloud cover detection, but you can swap that out, make it a slightly different vision model, reassess different utilities, and maybe use that.
Yep. All right, I'll pause at this point. And then, Steve, you wanna take up?
Yes, unless Isla, you wanted to go ahead. Either way.
I didn't have any direct questions actually. I had one single comment. The very, very small nit. You mentioned that Augustine 2014, 2016, kind of like the basis of the planet scheduling. It's actually, in fact, not.
Yeah.
I don't know
know.
if that
Yeah.
matters.
As
Yeah.
soon as I said it, I was like, that's wrong. It's
Oh,
dead
okay.
wrong.
No, I don't even know if that matters, but like it's
Yeah.
just I just for sake of correctness, just
No, I
put it
felt
out
bad
there.
when I said it too, because I know that's not true, and you did like a complete rewrite of like what they left for you. I'm sorry.
Yeah, we never had access to that stuff. I never even saw it. I wish we had, but it is still a mixed interlinear programming thing that we developed in-house, but yeah, I wish we had Sean's code. It used to run really fast, so it's a pity. Yeah, you can go ahead, Steve.
Okay, I just had a few. So convince me why RL is going to do anything useful.
Why RL is going to do anything useful? If I go back to the RL can
See,
parameterize.
I warned you, Shreeyam.
I know. I think RL will be able to do a few decisions based that the rule-based methods can't do. So, for example, if it's advantageous to do not one but two, three, four, five, unlike a rule-based method, it can actually pick for itself what it wants to do there. It can really nicely parameterize a lot of the set covering stuff, as I showed in the follow-up slides here.
But we have plenty of set covering algorithms. I'm completely unconvinced as to why learning is going to do better than a good algorithm on this.
What kind of algorithm would you suggest for this?
Any kind
Yeah,
of search-based
you're right.
algorithm.
Greedy set covering is actually fairly straightforward. But
Well,
greedy
no, forget greedy. I mean, any particular, like, well, I guess if you're calling it set covering in the space of what observations it's going to hit, yeah. I think any kind of reasonably informed, what I'm going to say, smart designed algorithm, I'm unconvinced. I mean, look, if you want to investigate it, I think that's your business. I can tell you in my team, the only reason why we're interested in some of these learning techniques is that we think that we could learn customized schedulers. So you might learn 100 customized schedulers for particular seasons, particular regions, particular things like that.
in my proposal, I mentioned time of day seasonality trends
Yeah.
and reinforcement learned heuristics as well. Sorry,
Yeah.
completely slipped my mind when you asked that question.
Okay, and then I have a side kind of like point. To me, the most interesting systems analysis would be comparing, let's say, a look-ahead instrument to a train to a geo for a single specific application, because that's kind of
had all the warnings.
yeah, because I think that's an actual, kind of like systems analysis that might actually occur, right, rather than an academic one. And in particular, I think there's been relatively little work in considering streaming near real-time geodata. So I think that might be quite interesting. But that's just kind of a side suggestion.
Steve, streaming it to the satellite or
No, so we did a study. You wouldn't actually stream it. You'd analyze it and then stream literally the minimum that the satellite needs because you're paying the ISL link cost. So for example, you might stream a binary cloud mask to the satellite for its upcoming underflight. And so it's a very, very efficient data-wise.
That's a really good idea. And I think if I'm going to go ahead and actually put in a model with goes anyways as part of my research, I think that's a system analysis that I could do.
Yeah, we also considered different kinds of storms. So now these geostationary satellites have these lightning sensors.
Yeah.
And so you could
Oh, cool.
also use those as analog problems.
Yeah.
The interesting thing is you can use those even if you don't actually have a true science application. You can say, imagine that I did want to somehow direct some narrow field of view sensor to wherever these lightning strikes were happening. This is how I would do it. And maybe someday a scientist will come up with, hey, I'd like to do this.
Yeah, yeah. Yeah, I had a backup slide for the coverage of some of these geo satellites. I mean, full Earth coverage at a cadence of 10 minutes is pretty unbeatable. It's awesome. Steve, are you
But
concluded?
other than that, all looks good.
Cool, thank you. Carrie, did you have your thought?
Yeah, I'm not sure if you can hear me yet, but I was gonna ask you about. Can you hear me?
Yep.
Yeah.
Okay, I was gonna ask you about prioritization in the downlink queue and image management and kind of data quality assessment while you're doing this, and how that factors in, because like Steve was saying, it's not necessarily a percentage coverage that matters.
Yeah. That's a good question. I think it depends on me finding a way to derive utility for each individual task, which when you work at Planet is fairly straightforward to do because you make money. Whereas when you're in academia, you kind of have to make up one of that utility function. Carrie, do you have any suggestions? Like I could do something like percentage cloud cover, some proxy that's just a randomly generated value or something like that.
Or I mean, even just recognition of targets that you're trying to capture and whether or not it's successful.
Right.
I would encourage not running down that rabbit hole. So, I mean, people have tried to define what like cloud cover really means for like decades, and they still have not yet succeeded. I will comment that using the Planet charging model is a little interesting because that's just what Planet, or I'm going to say most commercial providers have implemented some model, but that's not actually what the customer wants. And so there's some mismatch there.
Yeah. I
Yeah,
mean,
that's kind of what I'm saying, is like focusing on what the customer driven high value data is, and even if you have kind of vanilla templates for it, being able to assess whether or not you've accomplished a good capture of the target, or having some quality on that, and then what do you do with it? Is it flagged and then put in high priority in the downlink queue, or how does that managed? And how does that all fit in with your look ahead time and your cross links for whether or not you've accomplished the task?
That's a good question. I could probably accomplish that by considering the metadata, as Ishil said, say that a particular task is high value, and say that if I've observed this task and I've observed that it's cloud free, and I can take the image and then I can assign a high downlink priority to that.
What's interesting is there's like, we assign value like that to tasks in two ways. The taking or reaching the task as fast as possible, like reaction, that's like one value. That doesn't always mean that we also want to downlink it as fast as possible. It's usually the case, but sometimes like customers might be like, I just care that you take the image, and if it's cloud free, perfect. I don't really necessarily care when you download it. You can like wait, as like for a good ground station contact, and you can downlink it. And some customers are like, ASAP, downlink whatever you took. They don't care about cloud cover. I want to see it, what happens there, whether it's cloudy or not. I want the pixels, but get it to me as fast as possible, in which case it would go into the priority download queues on the spacecraft, which is the highest priority download queues. Like there's several queues, and then that's how you would slot these downlinks. Like, so there's the downlink priority, there's the tasking priority, or like imaging priority. There's two different main priorities that drive decision making.
That's interesting. I could do an approach where
I would say there's
sorry.
Yeah, I would say it's the acquisition priority, and then the acquisition urgency. to use the, decision theory, urgency versus importance, right? Your
Yeah.
acquisition urgency versus the data received urgency. Yeah. But I mean, I would encourage not getting too, again, this whole different models of utility is another rabbit hole. You could, for example, just demonstrate on more than one model of utility or almost two arbitrary models of utility, and then just disclaim that your method applies to whatever model eventually gets plugged in.
That is a good way to put it. Yeah, and being able to separate both of those actually is kind of interesting. I think that's probably as far as I'd like to go, but being able to separate those and have like a different utility function for the acquisition versus the downlink makes a ton of sense. Thanks.
Right. Does the committee have more questions, or do we want to open it up for a couple other questions before we confer?
I just have one other comment. Shreeyam, you should probably disclaim that you're not looking at multiple acquisitions of the same target in your model also.
Yeah, that's a good point. Thanks.
I guess, Shreeyam, could you go into a bit of detail? I like the timeline and responsiveness plot that you had. It's kind of like an earlier chart that's kind of a timeline of how quickly you need to respond. Could you comment a little bit about that, on how far you have to look ahead given LEO orbital velocity, and how much time you have to basically look at the look ahead and respond your tasking to it?
Carrie, you set this one up. Yes,
I
I
did,
absolutely can.
but it's important, right? Like
Yeah.
there's only so much time you have, right?
Yeah, so I did analysis on how much time you have for a look-ahead sensor, and I did a bit of systems analysis based on like the soft and hard constraints on this. I'm not going to talk about the soft and hard constraints. They're my proposal doc, but essentially, if you're looking, this is at an altitude of 500 kilometers. If you're looking as far off nadir as you can, right at the horizon, the maximum amount of look-ahead time you have is about, what is that? A little bit under 6 minutes. So just a little bit over 5 minutes here. For a more conventional look-ahead sensor like the one that I picked here, you actually only have about 50 seconds. So very, very quick.
So and in the 50 seconds you have to make you have to identify the scenario and then make decisions and get the spacecraft oriented and get the timing sequence set up. Can you talk us through that? What needs to happen in that?
Yeah. Okay. So in that time, assuming that you've already taken your look ahead sensor and it's at an angle of 40 degrees, this is also going to change depending on the attitude. It gets a little bit complicated, but essentially what has to happen is you have to take the image, you have to run your inference from your vision model, you have to geolocate those tasks on Earth's surface, and then finally you have to reassess the utility based on that observation, and then reoptimize the schedule onboard the spacecraft, and then executes it, which I agree is a lot and is really only suitable for the most agile and the most compute capable spacecraft.
I'll point out that if you look at your previous diagram of the different time scales like sensor web, leader follower, and geo and everything, in an ideal world, you could apply them all as inputs
Yes.
to your process.
Yeah.
Although that's a pretty dream-like vision.
I would like to also point out that there's also value in when you make that, you have that 50 seconds, you notice the clouds. There's also value in not taking the image. And that's even that is valuable. Like if you don't have time to slew and maybe take an alternative path, that's like valuable still. That's like brownie points. If you don't take the cloud image, that's still very valuable.
Yeah, that's a good point. It's not like the Mars rover schedule you demonstrated, Steve, where you have to wait for things to heat up, and that's really important. You can just essentially drop a task without.
Oh, I don't know. You probably have some sunk energy cost. I mean, I don't know how your imaging system works in energy, but yes, there's definitely some value. You're not going to create the data and yeah.
So quick question, Shreeyam. How could such a system help you? I know we're talking mostly optical imaging, but could such a system help you at night? And if so, how?
Yeah, depending on the phenomenon you're looking on, you could totally use some kind of thermal infrared sensor. Someone could. You could also go ahead and use different kinds of. I think the vision model is probably a bit misleading because you can apply it to things like radar. You can apply it to lots of different kinds of perception systems as long as you can derive some kind of utility function that you can then feed to your decision making.
Yeah, I think the SMICE's concept is not dependent on day. So it's a forward-looking radiometer to detect what looks like a deep convective ice storm, and then it's a special radar that interrogates the storm clouds. So that doesn't care about day or night, but certainly a lot of the applications are daytime.
Does that answer your question?
Sorry, I didn't hear that last one.
Oh, I was saying that for SMICEs, for deep convective ice storms, that's a day or night application. It doesn't matter. But yeah, they're definitely, most of them are probably daytime because those would be all the reflective instruments, right? That are looking at solar reflectance data. So yeah.
All right. Are we ready to have committee convene, or do we can probably take one or two quick questions if there are other folks who wanted to ask anything. Otherwise we can have committee breakout or committee stand and everybody else leave one or the other.
I had one question. Ishmael, which visualization did you really like?
It was the slew.
Oh, this one?
Yeah, that one. I really like that. Can I steal it? Thank you.
Sure, I'll send it to you. Okay. Anyone from the general public want to ask me a question?
Or you could explain what you did for this plot. It is pretty cool. So I'm not sure if everybody exactly understands what's going on here, but it's an important concept.
Yeah, so it's the idea that your spacecraft has a cross track and a long track, essentially projections onto the Earth's spherical surface. And what's happening here is that the spacecraft, starting at nadir, it has a specific swath that it covers on the ground. And using my perspective camera model, I can go ahead and rotate it. And using my world model, I can see at what point does it intersect with the Earth, and hence what is the track in terms of both a cross and a long track coverage. So depending on and I did something a little bit illegal here. I reversed my order of pitch and roll. You're meant to do your pitch and roll, but I reversed those to get the visualization that I wanted. So it pitches first, and then it rolls the spacecraft to show you the different amounts of coverage you get from that.
So Shreeyam, you should look at our Eagle Eye papers because we construct mosaics that are composites of these.
Cool.
To cover a ground projection polygon.
Nice.
So it really shows how completely messed up it is if you exchange nadir patches for off nadir patches.
Cool. Yeah, I'll revisit those. I think I skimmed them, but I'll be honest, didn't do a full deep dive. Okay, you guys all ready for breakout rooms? Cool.
Yes, I think so. I think now is the breakout time.
Cool. See ya. And I'll stop recording too.